Hello everyone, welcome back to some computational physics. So we're going to continue our discussion today of the ideas of trial and error, searching and data fitting. So today's lecture is mostly going to be talking about data fitting that we can do. So we're going to explore a couple of different methods. Well, we're going to explore one and introduce another, and then we'll get into that one more later on. But we're going to start off by just talking about interpolation. So let's say you have some table of values, and this is kind of a common situation you might end up with in the real world when you do measurements of different things. So if you are, say, measuring the speed of some object versus time, you'll end up with this table of values where you have the speed at a particular instant, right? So if we know that this is, say, some car that's accelerating from rest at a constant rate, we expect this to be purely linear data. So we can measure things, and we know the speed, at least to the precision of whatever our measuring device is. And it is possible that our measuring device is not completely accurate. It's also possible that there are other effects that take place, these so-called random errors in measurement that occur whenever you measure some quantity. So your real data is likely not going to be exactly linear, but you would expect it to be more or less linear. And if we look at this table here, we can see we have the speeds and kind of half-second increments. So what if we wanted to know the speed at, say, 2.3 seconds? We don't have a value for that, right? So you would have to figure out, well, how am I going to at least estimate what the speed was at 2.3 seconds? And, there are different ways that we could visualize doing this. One way is you could just say, well, let's take the closest value and call that good enough. But that's not very appealing for a number of reasons. It's going to potentially significantly differ from the actual value depending on how far apart your measurements actually are. And in this case, how quickly the vehicle is actually accelerating. So probably the simplest thing that you would want to do is called interpolation. And so interpolation attempts to account for the way that the values are changing over time, basically by connecting your known data points with some smooth function. So you can do this in a number of different ways. You can do it with any kind of smooth polynomial function that you want, and obviously the simplest would be a linear function, right? So for this particular case, we have a car that should be accelerating at a constant rate, and so we would expect that we would actually see linear data. So, drawing a line between two of our data points and using that line then to estimate the value might not be such a bad estimate, right? So we can see here is a plot, excuse me, of the data points. So we have our speed versus time on the x-axis, and 2.3 seconds obviously falls between 2 and 2.5 seconds. So 2.3 would be right here. And so, graphically speaking, if you actually plotted this out, you could just draw a line between them. And then based on this grid, you could actually just estimate what that value actually is. And so that would be kind of how things were done before kind of modern times. Also in this kind of simple case, since it is just a nice straight line, if we know the values of these points, then we can just compute the slope of this segment, right? And that slope of that segment would represent the average acceleration during that time interval, right? We could say, well, if we take the change in our speed, divide it by this half-second time interval. So if we go back, you would just take this 8.53 minus the 6.48 divided by 0.5, and that would give you an idea of the acceleration in between these two data points. Then we could use our kind of basic kinematics equation, take the speed at 2 seconds as our kind of initial speed, add to that the acceleration here multiplied by the time interval, the half second, or the 0.3 seconds to get to 2.3 seconds, and that would give you an estimate of the speed, right? Now, that's all well and good if these points are very well behaved, but if they have large errors associated with them, then connecting the data points could be significantly affecting your estimate. And so that might not be the best thing to do, right? So instead, we could do a best fit to our data. So this is just showing that for the data that we were just looking at, if we kind of estimate our acceleration in the exact way that we were just describing, where you take the average acceleration in the time interval and kind of assume it's a constant for that time interval, we can see that the acceleration varies quite a bit, right? So you have values here as low as 2.34 and as high as 4.51. So these are quite different values for the acceleration. And if the acceleration is indeed supposed to be a constant, then you wouldn't expect to see this kind of variation in your data. So instead of fitting just a line between two of our points, it may be better to find the line that comes as close as possible to as many of our data points as we can, and use that line to describe the acceleration for the entire period of the motion. So in this case, we have a very simple model, right? Our speed as a function of time is whatever the initial speed is, plus our acceleration times the amount of time. So we have just the equation of a line, right? So the acceleration is our slope, t is our independent variable, v is our dependent variable, and v0 would be our y-intercept. And if we know that we start from rest, that kind of puts some constraints on this v0. We could even hard code that constraint when we're doing our fit and just say that we have to fit the data purely with a slope times our independent variable. But in general, we have this, which we would call our model. So this equation here is our model. And the v0 and the a would be what we call our free parameters. So we can change the value of those parameters so that we can bring our line as close as possible to our data points. And so this is what that would look like. We will go over how this kind of fitting is done. So this is done via some sort of least squares fitting. And in this case, we didn't use any kind of error weighting when I did this fit. And like I said, we will talk about that more probably in the next lecture. So here we can see, you get this y-intercept value. We do find that the best fitting value is, right around 0. And we get a slope of 3.39. So that tells us that the acceleration that best describes this motion over the whole time interval is about 3.39 times the time here, t. And so that gives us this line. And then once we have this equation, right, so we've gotten the values of these two parameters. And in fact, in the way that I did this, I was also given the uncertainties on these parameters as well, which you could then potentially carry over into the uncertainty of your speed estimate, basically just all based on how well this line that we've drawn describes our data. And so here, once you have this, if you wanted to know the speed at any time, you would just plug that in, and this model then would be giving you your estimate of the speed at any time t. So those are kind of the two things that we can do in order to try to get information from data where we don't actually have actual measurements, right? So we can do interpolation or we can do fitting. And the one that you choose is going to depend a lot on the specific situation and what exactly it is you are doing. So the idea of fitting is usually what you're doing when you're actually very interested in the value of these parameters in your model. So you have some physics that you've worked out and you've derived that you think this model should describe what is going on. And what we actually want to see is what the value of these physical parameters happen to be. So that's when fitting comes in to use most often. So you don't have to, you're not necessarily trying to get some equation that you can plug numbers into to get values at points that you don't have data for. But what you're doing instead is actually trying to find the values of your parameters. And so this is something, say, when you hear about people measuring things like the Hubble constant or the dark energy density parameter, or any kind of fitting. Those are ones that stick out to me because I dabble in cosmology. So any of those sorts of measurements are actually where we've taken some model and we've fit it to our data, and then we're reporting the best fitting values of those parameters. And so that's where you typically use the kind of best fit. And then if you are doing simulation, oftentimes interpolation is going to be what you want to do, because in simulation you often will, for convenience and necessity, you will be creating values on some sort of grid, and you might need to then calculate a value away from the grid point. And so again, you can do many different things. The easiest is to simply take the nearest grid point value as the value that you use. But of course that has some drawbacks, and what you can do then is you can say, well, let's do either linear interpolation or some other sort of polynomial type interpolation of the data to try to get a reasonable estimate of values away from grid points based on how those values are changing at the grid points themselves. So now let's switch into actually talking about how to implement different types of interpolation. So the simple example we've looked at so far, we just have kind of simple linear data, right? It's data that we expect to behave linearly. And so drawing a line between two data points is probably not such a bad approximation to the actual behavior, right? So if you can assume that the acceleration should be relatively constant, so let's say that the car that we were testing is, say, an electric car, and we know that our electric car motor can output a constant force. So then we know that the acceleration should be constant, barring some other slight physical effects here and there. So, linear behavior then and linear interpolation is probably not so bad. But there's going to be a number of situations where our data is much more complex and varying in some other manner than just purely linear. And so when we do this interpolation, one of the things that we have to be careful of is to not introduce any kind of non-physical behavior by using a function that is more complicated than necessary. So when we are doing interpolation, generally, as you can see down here, what we're going to be doing is basically coming up with some sort of polynomial expression that will then pass through the actual data points that we have. So when we want to do this, we need to basically keep in mind that it's best to try to keep things local. And that's because the kind of complex behavior of our data points can be difficult to fit well with a polynomial. And so then as you're trying to fit that behavior over larger ranges of values, you have to introduce more and more terms in your polynomial. So you have to go to higher and higher order polynomials, and you might end up getting some kind of non-physical behavior, and we will see an example of that later on in this lecture. So that is one thing to keep in mind if you keep things local, so that you're only trying to draw some function between of order 3 or 4 of your data points at a time, and then only interpolating in that particular region, then that's going to give you much better results, generally speaking, than trying to create a single function that will describe the entire data set that you have. So let's say then, for kind of a more specific example here, we have some independent variable x, and we have tabulated values that we call xi, where I can be 1, 2, 3, and so on, however many values we have in our table. And we want to then also be able to describe some function g of x, our dependent variable. And we have measurements of this value, which we have these gi terms, which should be this function evaluated at the tabulated x values. So we can basically assume that we can approximate this function g of x as some n-1 degree polynomial. So n would be kind of our total number of tabulated values. And we say, well, maybe if we have, say, 10 values, then if we have a 9th degree polynomial, we should be able to get a curve that kind of goes through all of those points. And so this would be kind of that idea, this function here we write out all the way up to this x to the n-1. And then we would actually use our tabulated values, and when we plug in one of our tabulated values, we should recover the measured value here, right? That's what we want this function to do, and then we can use it to potentially calculate or get an estimate of what it would be at any particular point that we want, whether that's being at a data point or not. Okay. So again, if we try and keep things local, then this function should only be, second, third, maybe fourth order at most. And we would not expect it to work for the whole range of values, but just in that one particular range. And generally speaking, you also kind of want to stay away from the edges of your interpolated range. So one thing that we will look at later on in this lecture is instead of fitting a function to the whole range of a table, we will try to set up our code, excuse me, so that we can fit to a specific point, and that point could be some value. And what we're going to do is we're going to kind of try to find the closest tabulated value that we have, the closest tabulated independent variable that we have, and set up our interpolation so that the point that we're trying to get the value of is roughly in kind of the middle of the points that we are going to use. And then we can kind of stay away from the edges so that we don't end up introducing potentially unphysical behavior, because when you get to that kind of edge of your range, the function that you're fitting to these data points is no longer constrained anywhere beyond that last data point. And so you can start having behavior that shows up kind of on the edges that is not exactly what you want it to be. Okay, so the way to do this was worked out by Lagrange. He worked out a whole lot of mathematical stuff, and there's plenty of things that have his name attached to them. So he figured out a closed form expression to actually figure out what this polynomial should be. And so we first start by taking our g of x function and we write it as a sum of different polynomials, these lambda I here. So we have, g1 lambda 1 plus g2 lambda 2, so on, all the way up to gn lambda n. And these lambdas here can be computed as this product that we have shown here. So you take the x where you're trying to calculate the function, we subtract out this xj, and so j is what we're taking this kind of product here over, and I is of course whatever one of these that we're trying to compute. And so then it's relatively simple then to write out these terms and just do the multiplication. The textbook does go through a specific example for, I think, 4 points of data, and they show actually explicitly computing all of these lambda if you want to take a look at that. We will look at the code and how to implement this numerically speaking. So we can then say, well, if we have this and we have 3 data points, then what this is going to give us is a second degree polynomial, right? Because we kind of skip one of those data points, right? So this product here, we start at 1 and we go to n, but we skip the one where j is equal to I. Okay, so that's what this is telling us to do. And there's no restriction in this that our points in our table be evenly spaced, and that is important because there are some methods that rely on that even spacing, and in some cases that even spacing then allows kind of a big speed up of the algorithm because it becomes much easier to locate what the closest tabulated value actually is, right? So if you have an even spacing between all of your data points, if you take the particular x that you're trying to fit to, and we divide that x by the spacing between our data points and we first subtract out the lowest value of our data points, and then you divide that difference by the spacing. And then the space, when you do that, you get, if you take the integer return of that, you essentially get the array location where the nearest value to x actually is. And so if you have a large amount of data, if it's evenly spaced, that can really kind of speed up your interpolation because you can quickly compute the kind of nearest values, and you can then do your kind of local splining around those values and then get your estimate of your function anywhere that you want in that range. But in this kind of general form, we don't actually have to have the points being evenly spaced, and that can also be useful for real data. So in kind of interpolation and simulations, you can generally set things up so that your grid points are evenly spaced, and in fact you oftentimes want them to be, and so then you can take advantage of that kind of potential speed boost, whereas with real data, oftentimes your measurements happen to be wherever your measurements happen to be, and those points might not be evenly spaced, and so being able to do an interpolation that doesn't require this can actually be quite useful. So again, we usually stick to fitting kind of a small region of our table of values and not the whole table, and we will see exactly why later on. And another kind of important thing is that we can compute the kind of difference between our interpolated value and the actual function. If we know kind of the actual function and we can take derivatives of it, then we can compute this remainder. But of course, oftentimes when we're doing interpolation, we don't actually know what that function is. But it is possible to do this. And so one thing that this can be useful for is if you are writing your own implementation of something and you're trying to figure out kind of what the error you might expect would be depending on the specific behavior of your function, then you can, put in some test function that maybe more or less follows what you expect the data to be. You can take these derivatives and then you can do some kind of estimation for what you might want n to be in order to get a good result. And you would be able to see that maybe if you go too high into all of that, you would actually end up with getting larger errors, larger remainders by going to higher and higher n. And so that arises because we can see here if there are significant higher order derivatives, then our function might not be able to be calculated or approximated as a polynomial very well. Okay, so didn't get to that. So now we'll go and we will switch over and start looking at some code. So I'm going to switch this over here. So now let's take a look at actually writing some code that can do this sort of interpolation. Okay, so I'm going to open my file manager here. Then we're going to create a folder. And of course, it would probably be good to create a GitHub repository, but I'm not going to bother with that for now. But you may want to do that so that you have a good place to keep your code. So the first thing that we're going to do is we're just going to try to set up a quick kind of Lagrange interpolation code. And so what we're going to do that is we're just going to create a single file. We'll end up moving the important functions somewhere else later on, but for now, let's just create a Lagrange interp.py. Okay. And so again, you can follow along in Spider on your computers. You don't have to do anything special for this. This is all going to be kind of console-based code. We're not going to be creating anything complicated. We will create some plots, but they will just be kind of standard plots that will display perfectly fine inside of Spider. So we need to create a couple of functions here. So the first thing I'm going to do is I'm going to start creating this function called Lagrange interp. So this will be my Lagrangian interpolation function. And we're going to have x, the value that we want to compute our function at. So this will be some value in general that is not one of our data points. So we need to be able to find what that value of our quote-unquote function would be. And we're going to also here specify kind of the order of interpolation that we want to use. For this case that we're going to be looking at, we're just going to use basically all of the values. But later on, we will try to see about ways to modify our code in order to do it for just specific values of n. So here, this xi is going to be my tabulated independent variables. And before we go too far, Remember to make this a little bit bigger, so hopefully it's easier for you guys to read. So we have our xi and our gi functions here. And then from there, we need to think about what is it that our code needs to do, right? And so what our code needs to do is compute the sum of a bunch of those terms. So if we hang on just a second here, we can switch back over. So if we go back one, there we go. So what we need to do then is we need to compute each of these terms, right? And we need to do a sum of all of these terms to get our estimate of our function at that particular x. So that means we need to compute the lambda, and then we need to multiply by the appropriate g value from our tables, and then sum all of those up in order to do the interpolation. Okay, so to do that, then I'm going to create some variable here. I'm just going to call it val for the value of our function, and I'm going to initialize it to 0. And so this is going to actually just store our values as we sum them up, so that we can then return that in the end. And then we're going to have this for loop, and this is going to go over all the different points where we need all the things that we need to compute and actually do that computation. And you'll recall we had this condition that j cannot equal to I. So what I'm going to do is I'm going to put in this if statement here. And in case that is actually true, then I'm going to put in this keyword here called continue. And what continue is going to do is basically it's going to skip the rest of what's in the loop for that particular run through it, and then go back and continue afterwards. So this will skip explicitly that value of j equal to I. So if that's not the case, then we need to compute our lambda I and our we need to compute that, the lambda value. And I'm going to create another function, which I'm going to call lambda I. And this function lambda I is going to compute the actual lambda that we need. And so to do that, we need to pass the value of I, right? So that's what we're currently computing. We need to pass the value of n. We need to pass x sub I and x. And actually I needed, all right. Sorry, I was looking at the wrong spot in my code. So for this, we need to go over I, and this function lambda I, that was where that other code came in, and I'm not doing C++, so I need to not add semicolons. So sorry about that. So once we've computed that lambda value, then we take our table value and we multiply by the lambda value, and then we are summing those into our value. And then once we've done that, for all values of I, we return the value that we computed. And so now here is where we're going to define that lambda I function. So this is actually going to compute that lambda value. And so we pass the needed information. The particular I, so that particular location in our table that we're currently trying to compute this lambda for, the n, so that's kind of the order of the polynomial that we're going to be computing, or one higher than the order. The tabulated values of x, which we need in order to actually calculate the lambda, and then x, which we also need to numerically compute that value. So here, again, we're going to create some variable here to store, and I'm going to set this one equal to 1. And the reason we want to set this equal to 1 is because we're going to be performing a product instead of a sum, right? And so when we're doing the product, we're going to start with 1 so that our first term in the product is just going to give us, when we multiply this storage variable by that first term, it's only going to contain that first term, right? So this is then where we do our loop over j. So then we have 0 to n. And this is then where we check to make sure that j, when j is equal to I, that we don't actually do anything. And so again, that continue is going to just skip and then do the rest of the loop. And so what we want to do is we want to take our storage variable and then we're going to multiply it by the kind of next term in our lambda here. So we've got our xi j, so we access that list value, so that's our xj, and then we divide this by xii minus xij, and then that will give us the lambda I after we do this for all of the associated values of j, except for the one where it is equal to I. So basically, by having this continue statement, when we get to the point that j is equal to I, instead of coming down here and doing this, we just go back to the top of our loop, we increment the j, and then we start again. Okay, so once we have computed that, then we need to return that lambda I. Okay, so this is our implementation of this Lagrange interpolation, right? So we call this function, which then has this helper function up here to actually compute those lambdas instead of having them in here, which you could have put them all into a single function. There's nothing inherently incorrect about doing that. It's just that sometimes having things separated out in this way makes it a bit clearer as to what's going on, a bit easier to look at your code, and also a bit easier in the end maybe to debug because you don't have quite as many things going on. Oftentimes when you have, say, a double for loop in your code, as we do kind of hidden here, you can end up with problems, right? And so especially in Python here, where our white space, our tabs, are actual syntax, the more tabs that you have away from the margin, the easier it becomes to start making errors when we need to go back to a certain point before a certain tab. So by separating it out in this way, probably a little less error prone. Okay, so now what we're going to do here is, if you do take a look at the textbook, they work out a very specific example because it is one that you can actually compute the polynomial function itself by hand, which is what they do. And so here we're going to use that as a test case for our algorithm. So it's always good to have some sort of test case where you know what the answer should be, and then you can make sure that you get the correct answer when you run your code. And so here we're just going to actually have this code. We're gonna print the Lagrange interp. And so the first thing we're gonna do is make sure that we do get the appropriate value when we plug in an x that is one of our data points, right? So we know that when x is equal to 4, we should get minus 60 as our value. And if we don't, then that tells us that we've got a problem in our code, right? So this is a good kind of first test of our code, is to plug in 4 for our x. We also have 4 for our n because we have 4 values in our tables. We have the xi that we just defined and the gi here. So that's the tabulated independent variables and dependent variables. And then the book also prints out, actually gives you the value when we evaluate the spline at 0.5, which is, of course, exactly in the middle of 2 of our tabulated values. And so if you look in the textbook, you can find what this value should actually be. And so again, this gives us a nice little test case just to see if our logic in putting together this code is in fact correct. So now I'm going to open a terminal window here, and we will run this code. Make that a little bigger so that it's easier for you guys to read. So Lagrange interp.py. And so we get these 2 values, right? And you can see when we plug in x equal to 4, we do in fact get minus 60 for our value, which is exactly what we expected from our table. And if you look in the textbook, when you plug in 0.5, they also get minus 10.125 for that particular value, right? So, so far so good. It seems like our code is performing exactly as we would expect it. Now, what I'm going to do, since I have tested this, is I kind of want to decouple this algorithm from specific values, right? So these 2 functions here, which work in concert with each other, should work on any tabulated values. So we don't want them to be just like pasted into particular code. So what I'm going to do is I'm going to create a new Python file that I'm just going to call interp.py. And then in here I can put in all of the different kinds of functions that would do different kinds of interpolations. And so I can copy those over and have them in there ready to go in the case that I want to use them in different code, right? And so now I can take this file, and as long as it's in the same directory as the Python code that I'm working on, I can just import this into that Python project, that new project that I'm working on, and I don't have to rewrite this code. And this is, again, just to kind of stress this point, this is a very good practice to get into. So anytime you have code, any kind of functionality that you're going to be using very frequently in a number of different projects, it is best to have that functionality stored in such a way that it's in kind of its own independent file. And the reason you want to do this is as you are going through, you create this code once, you test it, you debug it, you make sure that it's working and that it provides reliable results. And then you don't have to ever test it again, right? You can just use it once you've gotten it working and you're sure that it's working. You save that time of rewriting the code and potentially introducing some bug that you then have to debug in your other project. So it is good to try to separate out functionality of your code into multiple files. Okay, so now we've got our interpolation algorithm there, all separated out. And we can then look at a more complicated case for actually doing this interpolation. And so this is the problem that is discussed in the textbook when they introduce this material. So this is looking for some resonant cross-section of a scattering that takes place. You can read about it in a bit more detail in the textbook, but for this particular problem and for this particular demonstration here, we are just going to look at this resonant cross-section. We're just going to use the data that they have, and we're going to actually do some interpolation on that data. Okay, so one second here, just need to rearrange some windows on my other screen. Okay. So what we want to do then is take that table of values that they give you in the textbook. Let me look up the actual table number here for you. So this is in chapter 7. And it is table 7.1. It's on page 151 of the textbook. And so this particular problem is basically, we have the cross-section for scattering of neutrons from a nucleus given in that particular table. And they give you an equation 7.21, which is the theoretical description of the data. And so that we will get back to that later on, because we can see what values for those parameters we get when we do our kind of best fitting. Okay. But for now, we will look at how to compute our resonant cross-section. So the first thing we're going to want to do here is bring in our old friend numpy. So we import that as np. And then we are going to want to import our interpolation library that we just created. And we are going to want to look at some plots, but again, these are just going to be kind of basic plots. So we will import our matplotlib.pyplot as a plt, as we usually do. Okay, so now I'm just going to enter those table values. So we have 0, 25, we have 50, we have 75, 100, 125, 150, 175, and 200. And then we're going to do the same thing again with our dependent values there. So we have 10.6, 16.0, 45, 83.5, 52.8, 19.9, 10.8, 8.25, and 4.7. Okay, so there are the values that are in our table, just transcribed over into our code. And what we're going to want to do here is basically we're going to want to compute this at a bunch of different x values. So we're going to want to interpolate from our data to a bunch of different x values, so we can end up drawing a smooth curve between them. And so you'll notice here I've put in that I'm going to create a numpy array, which is going to start at 0, and it's going to go up until this is actually going to give it basically up till 200. So we put in 201 because what it's going to be doing is it's going to continue looping until we get to a value that is not less than what we put here. So when we are at 200, it will still go through. If we put in just 200 here, it would loop, it would get to 199. And then when it went to check the condition after incrementing, you would have 200, which is not less than 200. So you wouldn't actually get to that value of 200. And we want to go all the way from the bottom of our table range to the top of our table range. And then we also have here the step size. And so I'm going to do this in steps of 1. I believe the textbook tells you to do this in steps of 5, but I find if you do it in steps of 1, it doesn't take all that much longer. Your computer should hopefully still do it fairly quick, and you get a much smoother looking curve out of it in the end. Okay, so the other things that I've just created here, so this is just an empty array that I can add values to, so that I can store those values as we're computing them without having to necessarily know the size ahead of time. I could do this differently. You can get the size of this numpy array and create another numpy array that is the same size, but this will work adequately for what we need here. And so then what I'm going to do is we're going to go over all those different x values that we have in our x array. So this is one of the things that we can do in Python when we are creating, when you have an array, is we can just write our for loop so that we go over each value in that array directly, and they will be stored. The value will then be stored in this variable here instead of some kind of loop control variable. So then we can get our value. So we're going to call our interpolation library here, and we're going to call that Lagrange Interpolation. And to that, we're going to pass that xi. We have 9 values in total. We're going to pass the list of values that we have there. And then when we get that value, we're going to take it and we're going to add it on to the end of our array. What I'm also going to do here is I'm just going to have it and go ahead and keep track of what energy has the highest value, this G max, where we can then say, well, that is clearly the resonant energy for this particular interaction, right? So the cross section is the highest at that particular point. And so that's what these two variables here, this x max and x min, the x max and g max, are going to keep track of. So then we can have what that value actually is, and we can keep track of the x where it occurs. Now, this isn't going to be perfect necessarily, because the xi that we get here is clearly, we're only going in increments of 1. So you might, in kind of a real sort of situation, if you were working with this data and trying to use this to actually get an estimate of the energy where this resonance occurs, you would probably start and do this in kind of steps where you first say, well, let's do across the whole range here with these kind of bigger steps of 1. And then once you've kind of narrowed in on where the maximum should be, you would explore a smaller range around where you expect the maximum to be, and then increment in much smaller steps just to see if there is a point where it is in fact a bit higher. Okay, so that is the whole loop that we need. So let's take a quick look and just kind of digest this code a little bit. So we have our tabulated values that we entered up here. we created an array of x values where we are going to compute our particular function here. So we're going to interpolate at all of these different x values. So you can see here we're going in steps of 25 in our table. And what we're going to get in the end is a function that goes in steps of just 1 in the energy. And once we've done that, this is just kind of creating our storage variable for the particular values. Then we have these variables here just to keep track of where the kind of resonance peak seems to be. And then we have our loop to go over all the different possible values in our X array. We do the interpolation at that value. We append that value to our G array, and then we check to see if we found a maximum. So here we just take the particular value and we say, well, if that value that we just calculated is larger than the value that we've stored in as the maximum value, then we come in here and we set our new maximum value to this value that is larger than the old maximum value. And then we just keep track of the X value that had that peak value associated with it. Okay. And so at the end here, we're going to have it print out the X and X value and the maximum G value there. And then we're just going to create our kind of basic plot here. So first we're going to have this plot where we just plot our data with circles here. And then we're going to plot our function. So these are going to be all the X that we have in this array here. We're going to plot against with the G values that we computed in our loop here. And for this one, we will have it draw a line between those points, and then we need it to show that plot. Okay, so that is then our code for this. So then we can say Python res cross and hit enter, and it will run. And so we can see this tells us that our resonance peak occurs at a value of 75, which has this 83.5 associated with it. If we look at our plot here, it does appear that maybe the peak is not quite on that particular point. So again, this is where we might go back in and say, let's look at a particular range in much more detail, right? But we can see that there are some kinds of issues here that we got by doing our interpolation across the entire table of values, right? So if we look near our endpoints here, and again, this is demonstrating a few things. So this is demonstrating why you would want to keep things local. So a better approximation here would probably be to just use these 3 data points in order to do this. So instead of using everything and trying to fit a single function to all of our points, if we just use these 3 points, we can probably find a curve that instead of doing this big spike up here, which is very likely unphysical and not actually what would occur, right? If you went to the lab and actually measured in this range, you would probably even be better off just drawing a line between these 2 points would be a better approximation than this kind of huge spike up. And also this little dip here in our values is probably not exactly physical. And then again, over here, we get this kind of little dip before this point, and then this kind of not as large, but a fairly large little spike up there. So this is probably not the best we can do for this particular function. And this is when you do need to, again, kind of be cautious in how you approach these sorts of problems. So let's see the simple thing that we can do, because this is one of the things, this is kind of following along section 7.5.1 in the textbook there. So this is assessing this Lagrange interpolation algorithm. And so one of the things that it wants you to do is to use our graph here to deduce the resonant energy ER, the peak value for that, and gamma, the full width at half max. So what we can do is first let's just try to locate that peak value. And so now we know, based on our run here, that it's around x of 75, right? So instead of computing just in increments of 1 there, we're going to want to compute around that peak in kind of finer detail to see exactly where this function peaks. And it looks, based on our graph here, let me pull this up and make this a bit bigger. So if you look closely here, you can kind of see the peak seems to be just before this data point. So our function kind of goes up and cuts through there. And since it's starting to decrease right after that data point, it looks like the peak is going to be somewhere just before that. So what I'm going to do is instead of just having this, right, so we can come down here and we can say for xi in, well, let's create a new x array here. Let's see, what should we call this? Let's just call this xj, I guess. Don't really like that name, but it doesn't really matter. So we're going to arrange, and so what we can do, since we've computed the x max value, we can actually set this up to automatically take whatever that x max value was and explore some range around that in much more detail. And since we were going in increments of 1, we know that the peak really should be somewhere within the increment kind of 1 to each side. But just to make sure that we capture that peak, we can take from x max minus 5 and maybe go to x max plus 5. And then we want to go in finer steps than what we did before. So I'm going to go in steps of 0.1 instead of steps of 1. And then we will create this gj, which again will be this kind of sort of array here. And then we kind of repeat our general process that we had before. So we're going to go through and do effectively the exact same thing. So I'm just going to actually copy and paste to that code because I've still called my loop control variable here, my iteration variable xi. And so then this just needs to have some minor changes there. So we just need to append to a different array. And so this will then create a different type, will give us a more accurate estimate, or at least the best estimate we can get from what we've done so far. And just because we're going to go ahead and also plot this particular function here, and we'll just let it automatically do the colors, and again we'll just plot with a line. We should see that this line more or less kind of follows along the line that we've already got on our plot. So we've created those modifications to our code, and let's see now what we get for that peak. And so we can see this is estimating that the peak actually occurs somewhere before 75, which is what it kind of looked like. And then we get the value for that resonance. And so there is our green line there, that's the new points that we computed this at, and we can see that does lie basically just right on top of that orange curve. And so then we would need to compute the full width at half maximum here. And so we could actually look at that. I think we will skip that for now and probably come to an end for this particular video. But there's one more thing that I do want to comment on a little bit before we end. That's kind of not directly related to this, but is kind of an important thing that I wanted to look at. So from here, if you want, you should try to continue through that section 7.5.1, where you then, instead of computing things across the whole table, you look at kind of more local fits. So you take, maybe 3 data points and you try to draw a curve that will fit through those 3 data points instead of fitting the whole table. And that should give you kind of more reasonable behavior on the extremes here. Right. So just one tip about that. One thing that you're going to need to do is when you feed in an x value, if we pull up our interpolation here, excuse me, when you feed in this x value, so you're going to have to modify this code, and you're going to need to locate kind of the nearest data point you have to the x value that you're trying to fit to, so that you can take then that nearest point and then the neighboring points on either side to actually create your function to do the interpolation around those particular points. So that is something to keep in mind, and the easiest way to do that is going to be to use the minimum function. So I want you all to kind of do some Googling on your own and try to figure this out. Basically, you can take the difference of this x with all of these xi, and do that using kind of a single line sort of situation, and then find the minimum value in that difference array, and then that will give you the closest point, and I believe should be kind of the most efficient way of doing that. Now, the last thing that I wanted to discuss is, so if we switch back over to our slides for just a minute here. So then let's see. So here we so for these slides, I clearly generated some data here, and I've stressed before this kind of importance of having a test case where your answer is known, so you can see how well your particular code is functioning. And so in order to generate these plots, then I created some code that created fake data, right? So that is something that is done kind of increasingly in the physics communities, is that you actually create fake data where you know what the result should be, and then you can test your whole data processing pipeline to make sure that you do recover the correct answer in that case. And if you can recover the correct answer in that case, the idea is then that you're likely to be able to recover the correct answer in any case, right? So if we switch back over here, I believe I put this code somewhere on my computer. Yeah, so I created this little program here in C++ to create this fake data. And of course, in this particular case, I didn't want to have just data that was a nice straight line, because that's going to be too simple. And then your linear interpolation between any two of those points, if your data is exactly a line, is obviously going to give you the correct result. And so we wanted to see something more realistic. So we wanted to build in some uncertainty to our data. And this is actually the incorrect code. I had a corrected version of this and I just grabbed the wrong one. But so what this code does is I said, well, I just did a Google search. I found kind of the average 0 to 60 time for cars in the United States, and then used that to compute the constant acceleration that would give you that average 0 to 60 time, and converted it to meters per second. And so that's what this 3.35 is. And so that's the actual acceleration that I put into this code. And then I'm computing things here again in these time steps of half a second. I've got this function here which just returns our linear velocity at a given time. And so I've got some storage here. And then I'm creating this random number generator here. And I'm having this random number generator actually give me a normal distribution or a Gaussian distribution. And so as I'm plugging in values to this, it will give me a bunch of random values that would fit to a Gaussian. So if you drew a bunch of them, you did a histogram, you would get a Gaussian distribution for those values. And so what I'm doing here is basically setting things up so that I'm saying that I have kind of Gaussian errors on all of these data points, and that the sigma associated with those is 0.05. So when we create this normal distribution here in C++, we put in the value that we want our distribution to be centered on, and then we put in the variance that we want, or the standard deviation that we want in that particular distribution. And so this is setting my kind of standard error that I want in my velocity measurements. And so what I'm doing here is then I'm saying, okay, so for the first thing I'm going to do is I'm just going to store kind of the current time of the little simple generation here, this little simple quote-unquote simulation. And then I'm calling this function here, which just returns my velocity. So we can set the initial velocity to 0. We've set our acceleration, and we plug in our time. And then what we're doing is once we've gotten that velocity, we are adding this random value drawn from this Gaussian. And so by centering it on 0, this is sometimes going to return positive values and sometimes return negative values. And then we can take those values and we just add them, and so it will either reduce or increase the velocity measurement by some kind of random amount that in the end, if you did this a bunch of times, you would get a distribution of velocities at that particular time centered on the value from our simple physics equation here, and with some small width to that distribution. And then we increment our time and we repeat that. And then this part here just outputs that data to a file so that I could process it later. And so here we can see, okay, I've put in this acceleration of 3.35, right? And when I did my best fit to this data, if we switch back over here, we can see I got 3.39 as the acceleration from this best fitting line. And so that is kind of within that like 0.05 margin of the actual value, right? So we did kind of reliably recover, or at least more reliably recover that particular value, especially compared to, if we go back here, you can see some of these are very, very far from that 3.35 value, right? So 4.51 is very, very far from 3.35. And you would be better off in this situation than using this, which, while it's still not entirely accurate, is at least much closer to the input value. And so this again is kind of highlighting that importance of being able to have a test case where the answer is known, because in this case we would see, okay, well, we are actually based on this fit, we're actually getting some value that's not quite correct. And we might see that if we actually put in the uncertainty of all these data points and we use that when we were doing our fitting, which again is something we will likely discuss next time, we would see that maybe we get a little bit closer, or that our uncertainty on this is actually a bit more reasonable. I didn't actually put in what these uncertainties were for this particular plot, but we can in fact see that we got something at least reasonably close to the expected answer. And so that does tell us that the algorithm that was used here is at least reasonably reliable. Okay, so before this video goes too much longer, we are a little bit on the long side, I will end things here. So again, I encourage you to take a look at the parts of that section 7.5.1 that we have not discussed here. I will discuss them kind of briefly at the beginning of the next video. We also need to discuss the cubic spline method, which is kind of a very common way of doing splines. It gives very, very good behavior between our data points. And then we will go into the idea of least square fitting in order to do our fits to data, which can be much better in the end than doing just interpolation. So I will see you all in the next video.